Okay, I think we can start. Do you have any questions so far? No? Okay, so in this second session, I would like to discuss with you some frequentist approaches to structured learning, or at least some of the most popular approaches for frequentist estimation in Gaussian graphical models. Okay, so let me start by saying that we can distinguish between DAG and UG model selection, and that for DAG model selection, there are traditionally two types of approaches that you also discussed yesterday. Two classes, we can say, of approaches. The first one is represented by constraint-based methods, while the second one is instead based on score-based approaches to estimation. Among the first, a common feature of constraint-based methods that the DAG estimation, or the estimation of the representative essential graph, is performed by applying a sequence of conditional independence tests. Okay, so if we know the relationship between conditional independence in the graph and in the joint distribution, that if we have some data, what we can do is to test for conditional independence between variables, and then based on the result of this sequence of tests, what we can do is to recover a graph structure. Okay, so examples here are the very popular PC algorithm, which, as we will see, output a essential graph estimate. Okay, so the representative of a Markov equivalence class. Okay, and this is implemented for categorical data. For Gaussian data, there are also extensions to ordinal data. We will mention something later on. Okay, then among score-based methods instead, what we need is to define a score, okay, for a graph, okay, a DAG, or again, it can be also a CP-DAG or an essential graph, and this can be based on a penalized likelihood, okay, where penalization means that we would like to favor simpler models, where simple means with a small number of edges, okay, to ease interpretation, or again, to recover something which is sparse, okay. Okay, and then we can apply this score on an algorithm, a search method, in order to identify the graph, the DAG, having the highest score. Okay, and examples in this framework are the greedy equivalence search by Chickering, which is designed over the space of essential graphs, so Markov equivalence classes, or what you also introduced yesterday, the hill climbing algorithm that can be applied to categorical, to Gaussian data, and I think even mixed data, okay, simply by defining a suitable score, okay. Okay, for model selection of undirected graphs instead, again, even in this setting, there are many approaches available. Commonly, these methods are based on lasso type regularization. Okay, so the idea is to do some shrinkage on the precision matrix, again, to favor zero entries corresponding to missing edges in the graph. And a very popular example here is the so-called graphical lasso, or graphical lasso, as you prefer. Okay, which is an extension of the lasso method to graphical model selection. Okay, so the lasso method which was introduced for linear model selection. Okay. Okay, so let me start from DAG model selection and from the PC algorithm. Okay, so the PC algorithm was introduced in 2000, and it is a constraint-based method which outputs an estimate of an essential graph. Okay, this is based on three main steps, which are the following. So we will start from an undirected graph, okay, and in particular a complete undirected graph, which means that all nodes are connected. Okay, so it is a full graph with all possible connections. Then we would like to start by removing edges, okay, based on conditional independence tests, and then possibly by setting these structures, which are a distinctive feature of an essential graph, in the subsequent steps. So in the first step, we would like to identify the skeleton of, say, the true DAG. Okay, so an undirected graph, which is not complete anymore because we want to remove something based on some conditional independence statements, okay, which should be the skeleton of the true DAG, so an undirected graph. Then, on this skeleton, we would like to to insert these structures. Okay, so we will start by directing some edges, okay, in this undirected graph. And this is step 2 of the algorithm. Finally, as we saw even in the example that I showed you before, when we saw an instance of essential graph, there may be edges that are directed in the essential graph, although they are not directly involved in these structures, if you remember, okay? So in the third step of the PC algorithm, we will try to orient other edges, if this is possible, okay? So, for example, as we will see, edges whose orientation avoids these structures, which have not been identified in step 2, okay? So still there are some edges that we can orient, although not directly involved in these structures, and at the last step, we will try to put these directed edges on our partially directed graph. Okay, so basically, conditional independence tests are only implemented for step 1, okay, so only in order to identify the skeleton. Okay, and the conditional independence tests of the PC algorithm are of, let's say, pairwise type, meaning that we would like to test for independence between two nodes, so U and V, okay, two single nodes, given a conditioning set, say, capital S, okay, which instead we can vary of having different dimensions. Okay, so let me exemplify how the PC algorithm works by considering the following example. So we have a DAG, which is, say, the true DAG, so what at the end we would like to recover, but we know that the PC algorithm does not return a DAG, but the representative essential graph. And the representative essential graph of this DAG is the graph G that I reported here, okay? So it is partially directed, it has a V structure, 2, 3, 4, and then there is an additional edge, which is directed, although not directly involved in a V structure, which is 4, 5. Okay, the reason why it is directed is, can you guess what is the reason here? If I have, instead of 4, 5, 5, 4, I would create what? An additional V structure. So I will break the Markov equivalence. I will fall outside the equivalence class. Okay, so this edge must be directed in all DAGs within the equivalence class represented by G. Okay, and we will identify 4 to 5 in step number 3. This is another edge which we can orient, although not directly involved in a V structure identified at step 11. Okay, so step number 1, we start from the complete UG. Okay, so an undirected graph with all edges that are connected, with all possible connections. And then what we would like to do is to remove an undirected edge between U and V if U and V are conditionally independent given S for some set S, okay, which is a subset of the set of vertices, of course, excluding U and V, okay? Okay, so if there is a conditional independence statement which holds between U and V for some conditioning set, we will remove an edge, an undirected edge between U and V. Okay, so how this is done in practice, okay, and then we will see also in the code. So what we can do from an algorithmic point of view is to start from conditioning sets of size 0, and we can test if U and V are, say, marginally independent, okay, given the empty set. Okay, so if this is the case, we remove the edge, okay? Otherwise, we can move to conditioning sets of size 1, okay? And then what we test is something of the form U independent of V given Z, where Z is a single node, okay, a single variable, okay? And we will do this for each U and V that are still connected after step A, okay? And then if this happens for some Z, then we remove the edge. Otherwise, we go on and on, okay? So if we implement this kind of algorithm, then at the end, what we will be able to recover is an undirected graph, U, like the one which is reported here. okay, which is the skeleton of the DAG-D. Okay. Okay, and this is the only step which is based on formal conditional independence tests. All the rest, all the remaining part of the algorithm is something, let's say, more straightforward. Okay. So step number 2, we would like to put these structures on our undirected graph. Okay. So a candidate structure for being a V structure is any structure of this form here, where there are U and V which are not connected, okay, but they are both connected to Z, okay. Okay, so this is sometimes also called an undirected V structure, okay. Okay, so we would like to decide if this is a V structure, so whether to put or not a directed edge from U to Z and from V to Z, okay. Okay, now the idea is the following. In a V structure, U and V are not conditionally independent, given Z, but they are marginally independent, okay? And this is possible, for example, by using this separation or the moralization criterion by Lauritsen, okay? So the moral graph of this graph here is the graph itself. There are no paths from U to V, so they are marginally independent. And okay. Okay, so the idea is the following. If the missing edge between U and V was identified from a conditional independence test of the form as before, U independent of V given S, and Z was not in the conditioning set S, then this implies that U and V are marginally independent. Okay, they are not conditionally independent given Z, but they are independent because there was a missing edge. And so we can establish that a V structure is present between U, V, and Z. Okay, and so we decide to orient our undirected V structure as a V structure. Okay, so this is still based on the outcome of the previous step of the algorithm. Okay, simply by looking whether Z was or not in the conditioning set which made U and V independent. Okay, if it was not, U and V are marginally independent. They are not conditionally independent given Z, and so this is a V structure. Okay, so at the end of step 2, what we obtain is what we can call an undirected graph with these structures. Okay, so it is in practice a partially directed graph that we can call U star, which is the one as before with some additional V structures, like for example 2, 3, and 4. Okay. Okay, now last step is exactly what I mentioned before. So there are other directed edges which are not directly involved in these structures, okay, that we can identify. And in particular, those edges are exactly those that, if oriented in a way or in another direction, can produce further V structures which have not been identified at step 2. Okay. Okay, so in practice, we need to look for all edges that are undirected, so of this form, AZ, where in particular Z is involved in a V structure, okay, for example 4 here, okay, and A is connected to Z, okay, so an example is indeed 4, 5, okay, so 4 is what we can call Z, U and V are 3 and 2, and what we call A is node number 5. Okay, so if we have this kind of structure, then we can orient the undirected edge between A and Z as Z to A, okay, which in this case is 4 to 5, okay? And the intuition is, as before, if we orient in the other direction, we would introduce another V structure, okay? Since A is not connected with U and V, okay, so we would introduce another V structure. Okay, so at the end of step number 3, what we recover is an EG estimate, okay? So a partially directed graph, which is the essential graph representing a Markov equivalence class of DAGs. Okay, so this is the general steps of a PC algorithm that can be applied to different types of data, okay, Gaussian or categorical. There are properties of this algorithm showing that if the sample size is large enough, then the PC algorithm converges to the true Markov equivalence classes. Okay, so for a reference, you can look at the paper by Kalish and Buhlmann, which is a more recent implementation of the original method of Speartes and co-authors, 2000. And then, of course, there are assumptions that must be satisfied. For example, one is faithfulness. So we must assume that there exists a distribution P, which is Markovian, which is Markov with respect to a DAG. We need to assume that samples are IID. Okay, otherwise we cannot implement what we will do as a condition independence test, or we need to adapt the type of independence test based on the assumption or not of identical distribution. And then another assumption is that there are no latent variables, okay? Otherwise, we may fall to recover the true Markov equivalence class. Okay, if some of these assumptions are violated, there are extensions of the PC algorithm which are more general ones, but that we will not discuss in this module. Okay, now depending on the type of data, we need to choose a suitable conditional independence test. For Gaussian data, conditional independence tests are based on partial correlation coefficients, okay, and this is exactly what we will discuss. While if you have categorical data and you want to apply the PC algorithm, you can rely on G tests of conditional independence, which are a sort of chi-squared test for contingency tables, okay? I don't know if yesterday you saw the PC algorithm for categorical data. Yes, no? Okay. Okay, but I will mention this in the R code. Okay, if you have categorical data, you just need to set a parameter saying, I would like to use as conditional independence test a chi-squared test or a G test of conditional independence. Okay, the chi quadrato that we all know, for example, for contingency tables. Okay, but let's focus on Gaussian data. Okay, so for Gaussian data, we can use a test based on the so-called partial correlation coefficient. Okay, and in particular, we will need the partial correlation coefficient between two variables and given a suitable conditioning set of variables, what we called S before. Okay, so in general, we can define the partial correlation coefficient between U and V and given, let's assume for now, the rest, all the remaining variables, okay, as this quantity here, which is given by minus the ratio between omega uv square root of omega uu times omega uv. And what are these omega elements here? These are exactly the elements of our precision matrix omega. And in particular, omega uv is the element at position uv. And we know that these elements is equal to 0 if, and only if, in a Gaussian setting, U and V are conditionally independent given the rest, given the remaining variables. Okay, so this is exactly that quantity that if it is 0, then there is a missing edge, there is a condition independence. Otherwise, it would be different from 0. Okay, and the denominator you have instead the diagonal elements omega u and omega v. Okay, so this is in general a partial correlation coefficient. In particular, in the PC algorithm, we require partial correlations between U and V given a conditioning set S. Okay, so something of this form here for some set which can be of sites 1, sites 2, and so on. So in general, a subset of the set of vertices except for U and V. Okay, so in practice, we can recover this partial correlation coefficient starting from the marginal covariance matrix sigma UU, where U is the union of UV and S. So only those nodes that we are interested in order to look for our condition independence with submatrix, and then taking the inverse, okay, of sigma UU. Okay. So starting from this matrix, we can define our partial correlation coefficient, and then we can implement a test based on this statistic. Okay, so the hypothesis test based on partial correlation coefficients can be framed as follows. We have a null hypothesis saying the partial correlation coefficient is equal to 0, that is missing edge, versus the alternative, which is instead the partial correlation coefficient is not equal to 0. Okay, so there is an edge between U and V. Okay, so in practice, one can use the Fisher-Z statistics, which is defined as reported here, as a statistic for this test, okay, which is the log of 1 plus, the sample partial correlation, rho hat, divided by 1 minus, again, the sample partial correlation. Okay. Okay, and this is something that we can compute from our data, starting from our sample estimator of the correlation. Okay, and this is it can be shown that it has a normal distribution, okay, with some standard deviation, which is 1 over square root of n minus size of s minus 3. So at the end, if we take this quantity here, okay, square root of n minus size of s minus 3 times the absolute value, then what we can do is to accept the null hypothesis H0 if this quantity here is smaller than phi minus 1, 1 minus alpha 2 as in a standard test, okay, based on a normal distribution, where phi is the CDF of a standard normal, 0, 1, n is the sample size, and alpha is the suitable significance level for the test. Okay, so in this case, we accept the null hypothesis, meaning that the two variables are independent given S, and so we can remove an edge between U and V in step 1 of the PC algorithm. Okay, so let me show you our implementation of the PC algorithm for Gaussian data. Okay, so as a starting point, I will use the simulated data that we generated before. Okay, and then a function for the PC algorithm is implemented within the package PCAlg. Okay, and it is called PC. So the main arguments of this function are 3. The first one is a sufficient statistic, okay, which is the one used to compute the test statistic, okay, which for Gaussian data is the sample correlation matrix, okay. So what you can compute by doing a core of X in practice scenario. Okay, this is not enough. We also need the sample size n. Okay, and this is the first argument. The second argument is instead the type of independence test that we would like to implement, and this depends again on the type of data that we have at hand, which for the case of Gaussian data is Gauss CI test, and which is exactly the one based on partial correlations. Okay, finally, as in any test, we need to fix the significance level for the test, alpha, which for example can be 0.01, 0.05, or whatever. Okay, and then among the arguments, there is a last one, which is called verbose equal to true, that if you set it, this is interesting, you will see exactly all the outputs, all the p-values in particular of the tests that are performed. Okay, so you will see exactly what are those tests leading to the removal of an edge, okay, as we will see later on. Okay, so we can apply PC function, which is provided by the package PCAlg, okay, by setting its arguments as reported here. You see, for example, the sufficient statistics, which should be a list with the sample correlation matrix core of X, which is called capital C, and the sample size n, which is instead the number of rows in the data matrix. Okay. Okay, so this is what I meant before. If you look at the output, which is provided here, this is exactly what I was saying. The PC function is testing for conditional independencies between pair of nodes, which are called X and Y here, and with which conditioning set, starting from conditioning sets of size 0. Okay, so S at the very beginning is equal to the null set. Okay, okay, and then whenever you have a p-value which is let's say greater than 0.01 or your alpha level, you will accept the null hypothesis saying that there is no edge between X and Y. So you remove the edge, you accept the null hypothesis, or you don't reject the null hypothesis, okay, to be more precise. Okay, and then if for some other edges the null is not accepted, say, then the PC algorithm will move to conditioning sets of size 1. And then, for example, we'll ask for, is 1 independent of 2 given 3? Okay. It will perform the test based on partial correlations, and then it will proceed on and on. Yes. I would say that in the original version of the PC algorithm, it does not account for multiple testing issues. There are for sure more recent versions that try to address that issue, but in this original version, it doesn't care about that issue, but of course it can be an issue. Okay, and then at some point the algorithm stops and recovers an essential graph estimate. Okay. Okay, so the essential graph estimate is the object called graph, which is within what I call PCFit 0.01. Okay, which is something that we can also plot. Okay, and it is this one. Okay, so this is an essential graph. It is a partially directed. In this case, it is completely undirected graph, but we know that the essential graph representing the true Markov equivalence class of the DAG, or the Markov equivalence class of the true DAG, was an undirected graph. So in this case, it works. Okay, and this is the resulting estimate. Okay, then you may consider different significance level for the algorithm just to check if you obtain something which is, let's say, robust with respect to the alpha level. Okay, where the effect of alpha basically is, you know, on the sparsity of the graph. Okay, because if you change alpha, basically you change the probability of accepting or not the null hypothesis. Okay, so this is something that you can use to control the sparsity of the graph. If you consider a very small value of alpha, you will favor sparser graphs. Okay, otherwise, if you increase the value of alpha, you will obtain something which is less sparse. Okay, so if you want to control for sparsity, you can tune alpha. Okay, depending on your, let's say, prior expectation of sparsity in the graph. Okay, in this case, even if I set alpha equal to 0.05, what I obtain is still the same, and then you can play a bit with other alpha levels. Okay. Okay, now if you have categorical data instead, let me just mention that you can use the PC algorithm. You just need to be careful. The data set must contain variables in a factor structure. Okay, so not integers, not numerical variables. You must convert them into factors. And then in this case, the type of conditional independence test is called this CI test, which stands for discrete conditional independence test. Okay, and finally, the sufficient statistics for the test is the data set itself, plus the number of levels of each variable. Okay, so it would be a list with the data frame and a vector with the number of levels of the variables. For example, if you have binary variables 2, 2, 2, 2, or whatever. Okay, and then still you can use the function PC, which will recover an essential graph estimate. Okay, so as for Gaussian data. Yes.
How does the algorithm manage the, let's say, how does the algorithm choose the conditional set? Because, okay, this case is a very small example, but in a bigger example, it could be controlled for all the possible conditional set.
Yes, I mean, it can be computationally, let's say, unfeasible if you have even hundreds of variables. So the idea is to start from conditioning sets of size 0, okay, which is the start. So you consider all pairs of variables. Then you move to conditioning sets of size 1. And in practice, I don't know. In principle, you should consider all possible conditioning sets, so all possible nodes. So this is, let's say, in principle, how it works. I don't know if in practice there are some rules for which it stops at some point without considering all possible conditioning sets. Honestly, I don't know. But in principle, it should consider all possible conditioning sets.
I was thinking maybe about some let's say, okay, this conditioning set is somehow useless because I might expect that.
Okay.
From the graph info till now, that kind of conditioning set.
So a sort of constraint that you would like to put, saying, okay, do not consider this conditioning set or something. I don't know if you can control for that. If you can introduce your, let's say, in a sort of blacklist of conditioning sets or whatever. So I don't have an answer. I don't know, honestly. Yes.
Sure about the answer to the question, but very sure that the algorithm you have two possibilities, which was house or the conflict between different condition set that gives you different result of the same action. So I guess that you select multiple condition set, and then the resulting margin should be like the most frequent answer for each options. So adding multiple condition set is always something
Okay, so because the point is that you may have, let's say, conflict between answers from different conditioning sets about the identification of a missing edge or not. Okay, I didn't know it, honestly. Okay. Okay, so let's move to instead score-based approaches to DAG model selection. And in particular, we will focus on the hill climbing algorithm. Okay, so the common feature of score-based approaches to DAG estimation is that we require a score, okay, or a DAG. And the idea is to maximize this score over a space of graphs. And I use the term graphs because we may consider both the space of DAGs or even the space of essential graphs for some reasons that we will mention. Okay, so if we rely on the space of DAGs, then we have the hill climbing algorithm as one of the most popular. So the reference here is just for a practical implementation, but it was introduced many years ago. So in this case, the exploration, the search over the space of DAGs is performed using local moves, which are based on the addition, the removal, or the reversal of directed edges starting from a given candidate initial DAG. Okay, we must be careful because we would like to move over the space of DAGs, so we must check that by applying any of these local moves, what we obtain is a DAG. Okay, so we need to avoid cycles in practice. Okay, in the second case instead, we have methodologies, we have methods which are instead designed over the space of essential graphs. So in this case, I would say that the algorithm should be more efficient because the size of the EG space is smaller. than the space of DAX, okay? Because you are doing a partition of the DAX. But we have some complication which depends on the type of moves that we can implement. So the idea is, in this case, to do an exploration of a space, which is the space of essential graphs. And essential graphs are a bit more strange objects, right? They are a bit more complicated because they are partially directed, okay? So you can add and remove edges, but in this case, you can either add, remove, or delete, or reverse directed edges, or even undirected edges, or even these structures, which are a distinctive feature of essential graphs. But still, you need to guarantee that the resulting graph is an essential graph, okay? And although essential graphs are characterized graphically, okay, if you're interested in the details, the paper that I mentioned before by Anderson, 1997, provides a graphical characterization of essential graphs as chain graphs with decomposable chain components. So they are well characterized. From a practical point of view, from a computational point of view, it may be more complicated than check for acyclicity in a DAG, okay? So we have a space which is simpler, which is smaller, but we have conditions to guarantee in order to do the search over the space of graphs, which may be in practice more complicated to check, okay? Okay, so we will focus on the hill climbing algorithm, okay, which is, I would say, simpler, okay, at least to understand. Okay, so in general, in a frequentist score-based method, we need to set a score, which is typically based on a penalized likelihood. Okay, so there are different ways to penalize a likelihood. We can consider an AIC penalized likelihood, or we can consider a BIC penalized likelihood. Okay, so in both cases, what we consider is the likelihood function, okay, which need to evaluate at the maximum likelihood estimator of the DAG parameter. So let me call it theta in general. So it can be the parameter of a categorical, of a Gaussian, DAG, whatever. Okay, and then what we obtain is our likelihood fx given theta hat and the DAG itself, to which we apply our penalty, which can be the number of parameters or the number of parameters over 2 times the logarithm of n, which will lead to the BIC. Okay, and basically the number of parameters in a graphical model setting is the number of non-zero parameters. Okay, so the number of free parameters. If you think of, for example, a Gaussian graphical model, a Gaussian DAG model, the number of parameters would be the number of entries in the B matrix, so the number of regression coefficients, plus the number of conditional variances, which is still Q. So something which is related to the number of edges in the DAG, right? Okay, if you remember, and in the matrix B, we have non-zero if and only if there is an edge, okay? So this number of parameters implicitly controls for the complexity of the DAG, the number of edges in the DAG, okay? So this is a penalty which will favor simpler DAGs, so DAGs with a small number, say, of connections, okay? Okay, and then theta hat is the MNE of theta. And these are two scores that we can specialize to categorical as well as to Gaussian DAGs. And of course, we will focus on Gaussian DAGs. Okay, so we will start from the cell representation of our Gaussian DAG model, okay? And the reparameterization of our omega matrix through our two B and D matrices, okay, where B is our matrix of regression coefficients, while D is our diagonal matrix with the conditional variances. Okay, so we wrote the sampling distribution. We can write the sampling distribution under a Gaussian DAG model, okay, which will have a product J1 to Q. If we have IID data, then the likelihood function can be written as a product I1 to N. Okay, of, again, a product J1 to Q, thanks to the DAG factorization, of normal densities, one for each xij, okay, so observation I column variable j. Okay, given what we have the mean, which is, remember, our, say, linear predictor, okay, some regression coefficients linking the parents to the node j, times those observations in the vector xi corresponding to the parents of the variable, and then our conditional variance djj. Is it okay? Okay, so now, if we exchange the two products, I1 to n and J1 to q, what we can write is the following here, okay? Where in the parentheses, what we have is something which looks like a likelihood of a normal linear regression model, okay? I1 to n, normal densities for xij, a linear predictor, a conditional variance, okay? And we know how to deal with linear regression models in the frequentist analysis of a linear regression model. Okay, here the elements are the components of capital B with rows indexed by Paj, the parents of node J, and the column corresponding to the node J itself. So these are the elements playing the role of the regression coefficients in the Jth term, in the Jth equation of our structural equation model. Okay, so if we want to provide an MLE estimate of the parameters appearing in this likelihood, what we can do is to compute the MLE of a normal linear regression model, okay, that we can call B hat parents Jj, and the same for the conditional variance, the variance of the error term, what you typically call sigma hat J. Okay, and then finally, we can plug in these estimates in B and D, our two matrices, in order to obtain our likelihood, what we called before f of x given theta hat. Okay, so in this case, the theta hat is a pair B and D hat. And this is exactly the likelihood that we can plug in into the AIC or BIC here in order to obtain our score. Okay, so basically we can rely on standard results on normal linear regression in order to compute a score for a DAG, thanks to the DAG factorization. Is it clear? Make sense? Okay. Okay, so we have our score, which can be the AIC or the BIC. So we can implement our score-based method through a hill climbing algorithm. So how does the algorithm work? Okay, so this is the general form of the algorithm. Again, this can be applied to any type of data if you have a suitable score. Okay, and the steps are the following. We start from an arbitrary initial DAG, say D0, which can be, for example, the null DAG, a DAG with no connections, for example. Okay, and then the algorithm will output a DAG, so pay attention because the output is not an essential graph, it is a DAG estimate that we can call D hat. Okay, so step number one, let me call the initial DAG, D0. Then we start by computing the score of this DAG, SC of D. Okay, and then we would like to apply the set of local moves that I mentioned before, if you remember. Those that for DAGs are based on addition, removal, or reversal of single edges. Okay, of course, there are many possible moves that I can apply, provided that what I obtain is not cyclic, so it is a directed acyclic graph in practice. Okay, and then for every possible move, what I obtain is a modified DAG, for example, obtained by adding an edge or by removing an edge, and so on. And I can compute the score of this modified DAG. Okay, so if the modified DAG is D star, I will obtain the score of this DAG. Okay. Okay, and then if the score computed on the modified DAG is greater than the score on the current DAG, I will update my DAG, D equal to D star, and I will update the score. Okay, so as long as the score increases, I will go on and I will update by applying my move, my local move to the DAG, and by updating the DAG, D star. Okay, at some point, as long as the score does not increase anymore, I can stop the algorithm and I can return my DAG D, okay, which will be the ultimate estimate of the hill climbing method. Okay, so this is the very basic implementation of the hill climbing algorithm. Okay, okay, so let me show you in R how we can implement a hill climbing for Gaussian data. Okay, this is very simple. So as I was saying before, an algorithm for the hill climbing method is provided by the package by Scutari, for example, which is the BN learn package. Okay, so that we need to load. Okay, and then you will find a function called HC, whose main arguments are two arguments. The first one is the data matrix, which should be in a data frame format, okay, capital X. The second one is instead the score that you want to apply, okay, which should be a score for a DAG. The default score is the BIC, which is the one that I will use. Otherwise, you can customize the score if you want to use something different. There are even Bayesian scores that can be implemented within the HC, which are based on marginal likelihoods. Okay, we will mention something this afternoon. So you can even use a Bayesian score within, let's say, a frequentist algorithm. Okay, a frequentist methodology. Okay, so let me start by creating a data frame from X. Okay, and then we have the function HC, which will apply to X equal to X data frame. Okay, the default is the BIC, which is fine to our purposes. Okay, and this is the output. This is the estimated. This is the estimated DAG. It should be a DAG, probably. Okay. If I zoom out, I should see that there are edges. There are arrows between my nodes. Okay. Okay, the layout is just different because of the package implementation. Okay, then if you want to recover the representative essential graph, okay, because you must be careful, there is an equivalence class behind this DAG. Okay, otherwise you may find some misleading results in terms of directionality of these edges. You can do this using, for example, the function DAG to essential graph, simply by recovering first the adjacency matrix of this network. Okay, and there are functions to recover it. Okay, because this is another structure. It's not GraphNL. It is a BN learn object. So something which is different to deal with rather than GraphNL objects. Okay, but I think to our purposes, this is enough. Okay, any question? Yes.
Other versions guarantees like not getting stuck to local maps.
I think that common practice is to initialize the algorithm with different initial points. Absolutely. You may be stuck in local optimal, of course, because of the definition of the algorithm itself. So my, let's say, personal recommendation is to repeat the procedure more than once for different initial DAGs, okay? And then check for the results for the convergence. Yes.
And in your experience, which is more expensive between these?
You mean from a computational burden? Computational time. Honestly, I don't know, because I've never used either the PC or the hill climbing in high dimensional settings. So I think that if you have 100 of variables, the computational time may be more or less the same, provided that the algorithm converges, of course. Okay. Yes, the PC algorithm is quite efficient. If you have 200, 300, 400, it takes a few minutes to run, I think. So it is quite efficient. I don't know about the hill climbing because I never used it in real high dimensional settings. And then I'm a bit more worried about the convergence of the hill climbing if you have an high dimensional setting, because if you increase the number of variables, then of course the dark space is something very, very big. Okay, so you may experience some convergence issues in that case. So I would prefer maybe the PC algorithm. Other questions? Okay. So finally, let's move to the instead graphical lasso method, which is the one that I want to discuss for undirected graph estimation. Okay, so I think that you are more or less all familiar with the lasso method for linear model selection, right? For regularized linear model selection. Okay, so here the idea is very similar, and in particular, we would like to encourage some sparsity. We would like to do some shrinkage, not on regression coefficients, okay? We don't have directly regression coefficients, but on a precision matrix, remember. We'd like to encourage zero entries, so to do shrinkage on the elements of the precision matrix in order to identify a graph. Missing edges corresponding to zero elements in the precision matrix. Okay, so we can start from a Gaussian UG model, okay, saying that x1, xq given omega is multivariate normal q0 omega minus 1, and we assume that omega is Markov with respect to an unknown, of course, undirected graph G. Okay. Okay, then we assume to have IID observations and IID observations. Each one is Q variate, of course, x1, xn, that we can collect in the data matrix capital X. Okay, so if this is the case, as we wrote in session 1, the likelihood function can be written in this way here as proportional to the determinant of omega n over 2, the exponential kernel, 1 over 2 the trace of omega s, where s is the cross product between x prime x. Okay, so this is our likelihood function, and our goal is to estimate omega, which should be a sparse precision matrix. So a matrix containing as many zero entries as possible, say. Okay, and the idea of the graphical lasso, G lasso, is similar to the lasso for regularized linear regression. We want to encourage zero entries in omega, as we said. Okay, so a feature of the graphical lasso is that it performs both graph selection and parameter estimation. Why? Because in practice, you achieve graph estimation by estimating a sparse precision matrix. Okay, so you estimate a matrix. This matrix will contain zero entries, and based on the zero in the matrix, you will say, okay, the corresponding graph is this one. Okay, so basically, you induce a graph estimation using a sparse parameter estimation. Okay, so this is the idea. Okay, so the problem is, let's say, quite complicated. Okay, but it can be shown, okay, then I will provide you some references, that it can be framed in a similar way as the lasso for regularized linear regression. Okay, so let me start from the general problem. What we would like to do okay, in principle, is to maximize our log likelihood with respect to omega, to which we apply a penalty. Okay, so this is exactly as in the last for linear regression. Okay, and in the penalty term, what we have is a tuning parameter, as usual, say lambda, times the L1 norm of omega, which is nothing but the sum with respect to all the entries of omega except for the diagonal of the absolute value of the elements. Okay, so remember the intuition in the lasso type approaches. Okay, we would like to have this quantity as big as possible, okay, which means that we would like to have the likelihood, which is big enough, say, okay, implying that, okay, the fitting to our data is good enough, okay. At the same time, however, we would like to have the second term, which is minus lambda, the L1 norm, as small as possible, right? Okay, because we want to maximize this objective function. And how can we achieve a small value of the penalty term if the L1 norm is small? And the L1 norm is the sum of the absolute values of the entries of omega, okay? So something which is small if omega is sparse, if it contains as many zero entries, right? Okay, but if you put too many zero entries, then the fitting to your data may be worse, of course, and so you reduce the likelihood, right? So there is the trade-off, which is the usual one in the last type regularization, between the model fitting and, say, the model complexity, which is the one that we capture through the penalty term. Okay, so two things that we would like to balance. Okay, a good fitting and a simple model, a sparse model in this case. Okay, I was saying that the problem is quite complex in order to find for an exact form solution. Okay, the solution was provided in an algorithm which was proposed by Friedman et al. Okay, so the first thing that you can do is to write explicitly, for example, the log likelihood function. Okay, okay, which is nothing but the logarithm of what we wrote before here. Okay, and then instead of maximizing, if you like, you can equivalently write it as a minimization problem, okay, by writing minus the log likelihood, okay, and then plus your penalty term, okay, which perhaps looks more similar to the lasso regression problem. Okay, and then the next idea, let's say, is to translate this kind of problem into a collection of node-wise, which means one for each node, lasso regression problems. Okay, so problems which are exactly the same or similar to those in the lasso for linear regression. Okay, so I will provide you just, let's say, a general intuition and not too many details of the solution. But the idea is more or less the following. We can start by considering an initial estimate of the variance-covariance matrix, let's say sigma tilde, which is partitioned into 4 blocks, okay? Where the first block, okay, the one indexed by u equal to 1 is of size 1, okay? So we have this kind of partition, and we can do the same for S, which is our x prime x matrix. Okay, now, in this paper by Banerjee et al., it is shown that the graphical lasso problem is equivalent to this problem here, okay, corresponding to the minimization of a beta regression coefficient in this objective function, okay, which depends on small b, which is the product between the block of our initial estimate, sigma 1 tilde minus 1, and the sample x prime x matrix, okay? So something which depends on the data, okay? And beta, which is instead our regression coefficient parameter, okay? which is a function of the variance-covariance matrix, okay? And in particular, it can be written as sigma 1, 1 minus 1, sigma 1, 2 by properties of the multivariate normal distribution in the case of zero mean, okay? Okay, so this is instead a problem which can be solved using techniques which are very similar to those for lasso linear regression, okay? Where the objective of your estimation procedure is a sparse beta vector, sorry, so a vector of regression coefficients, okay? And this will be the first step of the algorithm, okay? In the first node-wise regression, okay? So the one for node number 1. Okay, then you can move to u equal to 2 and so on, okay, to other linear regression lasso, okay, so that at the end what we obtain is, if you iterate this procedure, a collection of regression coefficient estimates, okay, one for each node. And so finally what you can do is to recover your sparse inverse covariance matrix, okay? So simply by computing sigma 1, 2 as sigma 1, 1 times beta, okay? From the relationship here between beta and the variance covariance matrix here, okay? Okay, and in doing this, basically you are filling the elements of your estimated variance covariance matrix, sigma hat. And so finally you can recover omega hat, which will be the estimate of your precision matrix. Okay, so this is, let's say, the general idea behind graphical lasso. Okay, we can have a look at the R code for the graphical lasso, which is implemented in the package called glasso. Under the function which is called glasso itself. Okay, so the main arguments of the function are, let's say, two. The first one is the sample correlation matrix, which is called S. The second one is instead the regularization parameter, so what we call the lambda, okay, which here is instead called rho, okay. Now, there is a practical recommendation. So if you remember the lasso, this is very typical. It is very common to scale the variables, okay, in the lasso methodology. And we will do the same here. This is to achieve invariance of our coefficient estimates, to ease interpretation and whatever. So this is something that you can do by applying the function scale to the data matrix capital X, okay, which will center your data and will scale the variables, the columns, in a way such that we have variances, marginal variances, which are equal to 1, okay? So zero mean and the standard deviation equal to 1. Okay. So this is the scaled version of our data matrix. Okay, and then we need to compute the sample covariance matrix, okay, that we call capital S, cov of X standardized. Okay, so now there is a tuning parameter, as we said, rho, which, if equal to 0, will not perform regularization, right? So if we set rho equal to 0, which is our lambda here, basically what we obtain is a maximum likelihood estimator of omega with no penalty. And in which case, you can check it if you want, the estimate of omega will coincide with the sample precision matrix, okay? With no penalty, and in general it will be a matrix with no zero elements, okay? So with no shrinkage. Okay, what we are much more interested in instead is to do some regularization on omega, of course. And this is done, for example, by the function G lasso path, okay, where path suggests that we can run the lasso for a grid, a path of different values of our tuning parameter rho. Okay, and then of course at the end we need to decide what is the optimal one. We will say something at the very end. Okay, so if you apply G lasso path by taking as the main argument only the sample covariance matrix without explicitly setting rho, what you will obtain is a collection of estimated precision matrix for a grid of values of rho ranging between 0 and 1, which is the default. Okay. Okay, and you can check it, what is the default list of penalty terms that are applied, which is this one. And then what you can do is to recover the estimated precision matrices, one for each value of rho. Okay, so these are organized into an array, which is called W. Okay, so if you take the third component, if you set the third component of the array equal to 1, you will obtain the estimate of the precision matrix for rho equal to 0.1, which is the first value of the tuning parameter. And this is not sparse. You see that there is no zero entry in the matrix here, or at least no exact zero entry. While if you increase the value of lambda or rho, okay, what we obtain is that we are encouraging zero entries, and now we have zero entries in the precision matrix instead. Okay, we can go on. Okay, and then we obtain something which is even more sparse, perhaps. Okay, so with even more zero entries. Okay, so at the very end, the question is what is the best value of rho? Okay, as usual. Okay, so if you remember in lasso regression, we use cross-validation methods, right, in order to decide what is the optimal value of the tuning parameter. Okay, so here you can do something similar. Okay, so in the lasso, in the classical lasso, what you use typically is an estimate of the test error, so something that you can obtain from cross-validation by considering a test and the training set, or something even more complex. Okay, and then you can look for the value of your tuning parameter, minimizing the estimated test error. Okay, you obtain the minimum test error for the value of lambda, which is equal to 0.4, and you decided that that is the optimal value. Okay, so here we can do something similar. Okay, one possibility is okay, our estimation procedure is based on the maximization of a log likelihood function, right? So what we can do is to split our data set in training and test. Okay, so we fit omega on the training, and then we compute the maximized log likelihood function on the test set. Okay, by plugging in the estimate that we obtain using the training, right? As usual. Okay, and so finally what we can do is to identify the optimal value of rho of our lambda tuning parameter as the one maximizing the, let me call it, test log likelihood function. So the log likelihood function computed on the test set. Okay, so this is one possibility that you can implement in practice in order to choose the optimal value of your tuning parameter. Okay, I don't know if it is implemented in any package. Okay, otherwise you should run it by writing your own code. Okay, so let me provide you some references about what we discussed, and then since we have a few minutes, we can start with a brief review of Bayesian methods for structural learning. So basically, there is the paper by Chickering here, which is the one about the greedy equivalence search that we did not discuss, but it is a quite popular method, okay, that you may find useful. The other papers here are instead related to the graphical lasso. The one by Kalish and Ullman is instead for the PC algorithm, okay? While the last one by Scuderi it is the paper related to the BNLearn package, which contains a variety of these score-based methods. The hill climbing is implemented, even the PC algorithm is implemented, and even something more for mixed data, I'm sure. Okay. So in the last part, let me start by introducing, by doing a brief summary of some, yes.
Well-known problem of loss regression is that it might be strongly biased and also do not enjoy the Oracle property or identify. I mean, it's not guaranteed that the variables identified by the lasso are the true variables that affect the response. So I was wondering if there is some result about graphical lasso on this direction or not.
I'm not an expert of graphical lasso, so I don't know the recent literature on the graphical lasso, so I don't have an answer. I don't know results in this context by the graphical lasso. We can check, but I don't know honestly. Okay. Yeah.
This is what there were no causal interpretation. So the VCR with the causal interpretation is very neat.
It's very?
It's neat, with like the couple of like position. This problem applies in us basically applying any type of position if it's possible to position this.
By undirected graph, basically an undirected graphical model is a model of conditional independencies and stop. So you can read conditional dependencies. I think things are a bit more complicated than it seems to be. In the sense that if there is a missing edge, you can say that, of course, there is a conditional independence. You can say that there is not a direct cause. I may agree, because if there is no connection, there is not a directed edge even, but you cannot exclude that there is a causal effect, because causal effects may also propagate around paths. So even if you don't have a directed edge between U and V, there may be an indirect causal effect. Okay, but of course you must be careful when you have undirected graphs. So basically you're just considering observational data, and you are assuming you are just working with conditional independencies. If you want to do some causation, you need to use DAGs. You need to interpret the DAG from a causal perspective. So you need to do some assumptions, okay, that must be clearly stated. In that case, okay, I may agree with you that if you have a DAG estimate, so if you rely on a DAG, then under some assumptions, you can say something like, there is no path between U and V, so there is no causal effect, either direct or indirect, but conditionally on that DAG, then pay attention, because the DAG may not be identifiable. There may be another Markov equivalent DAG. So under that DAG, there may be a causal effect, okay, according to your own definition of causal effect, which again requires some assumption. So if you want to do causality, you should use DAGs plus some suitable assumptions, okay, which are the one introduced by Pearl based on the notion of interventional distribution and whatever. If you just want to do structural learning with undirected graphs, you just monitor, you just look at conditional independencies and stop. Okay, so without causality. And missing edges does not imply that there are no possible causal relationships. Okay, not direct maybe, but there may be something more behind. Okay.
There's just one thing about the initial procedure of the graphical lasso. So essentially, if I got it correctly, the thing I do is to use the partition of the matrix, the matrix.
Yes.
And then for each partition run a a lasso.
Yes, a standard lasso for linear regression, say, yes, and you obtain an estimate of beta. Okay.
And those regressions are not linked whatsoever. So it's just a parallel lab. So except
I think that they are in some way related because they depends. So each block depends on the previous one, for which you have an estimate at the previous step. Okay. So they are in a way related. So you start from u equal to 1, you obtain an estimate of sigma, and then you need this initial estimate for the second one because you are considering a conditional distribution given the node number 1.
So it's not like I start in my guess of the matrix, I run the regression and I read it and I run again in the regression is more like a calculation.
Yes, node by node. Yes, I would say yes. Okay. Yes.
So if I want to update the first block, I have to go through the matrix, for the whole matrix, and then start from the beginning.
I don't know if there are issues in the choice of the initial block. So for example, u equal to 1 means the node that we labeled as 1. Okay, but you can choose whatever you want, of course. So I don't know if in practice you can choose whatever and results are sensitive to this choice or things like that.
The optimization problem should be complex, so I think even if you start from anyone you want urgency, exactly on the global ones. I mean the L1 norm is complex, the likelihood is complex for the procedure, so global problem should be complex.
I don't know. Yes, I agree with you about the, yes, what we are saying is true, but I don't know about convergence issues of the graphical lasso in practice. If there are results or there are ways to check it in practice. Okay, any other question? Okay, so let me just give you some remarks that will be quite useful for the next session. So till now we considered frequentist estimation for either DAGs or undirected graphs, which were basically based on maximum likelihood estimation of DAG parameters under the Gaussian assumption. Okay, so now we will need to move to a Bayesian setting. Okay, so let me just give you some remarks about how to do model comparison, okay, model selection, if you like, in a Bayesian framework. Okay, so a very general framework is the following one. We consider, in a multivariate framework at least, a collection of random variables, x1, xq, and we'll assume to have IID q-dimensional observations that are collected in our data matrix, capital X, as usual. Okay, then we will consider a parametric model. Okay, so we will assume that f, the joint distribution of our variables under a model, say M, belongs to some parametric family, for instance, the Gaussian one, okay, which is indexed by a parameter theta M. Okay, and this parameter is specific of model M. Each model its own parameter. Okay, and this parameter lies in some space like theta M, okay, which is, for example, the space of SPD matrices Markov with respect to the DAG. Okay. Okay, so in a Bayesian model, what we have basically is a set of assumptions on the sampling distribution of our data, f of m. But this is not enough. We need some assumptions on the parameter, which are encoded in the prior on theta m. So we need to set the prior distribution on the parameter itself. And then if we want to do model comparison, model selection, what we will regard as uncertain as well is the model itself. Okay. So additionally, we will need a prior on the model, P of m. Okay. Okay, and this can be done under a given model, but we will regard the model as uncertain, okay? So in general, we can consider a collection of competing models, M1 and capital K, different models, for example, a collection of DAX. Okay, and in model selection, what we are interested in is a posterior probability for model MK given our data. Okay, so this is something that we can write using Bayes' theorem as proportional to, as usual, a likelihood function times a prior. The only difference is that since we are not interested that much in the parameter, the theta, okay, but just in the model, we want to do model selection and not parameter estimation. I will consider not the likelihood, but the marginal likelihood, what I call M of X given the model, times the prior on the model itself. Okay, so there is no theta anymore, but still this holds thanks to Bayes' theorem. Okay, something that if you want to compute it exactly, you need the denominator, which is the normalizing constant, which is the sum over all the possible models, capital K models, of the marginal likelihood times the prior. Okay, so this is the Bayes' theorem applied to model selection, okay, to Bayesian model comparison. Okay, so basically there are two main ingredients that we need in order to do Bayesian model comparison. The first one is the marginal likelihood of the model itself, okay, or marginal data distribution, those things that you obtain by integrating out with respect to the parameter. And the other one is instead the prior on the model itself. Okay, so the first one, as we said, is an integral of the likelihood function f of x given theta k, which is integrated with respect to the prior on the parameter theta k itself. Okay. Okay, well, the likelihood in particular, if we assume IID observations, can be written as the product I1 to n of sampling distributions evaluated at xi given theta k. Okay, so the main difficulty is that we would like to compute this integral in an analytic, in an explicit form. Sometimes this is possible, sometimes it is more complicated. In the Gaussian case, it will be possible. Okay, so as we mentioned this morning, we will have closed form results for the marginal likelihood by assuming multivariate normal distributions or graphical model extensions of the multivariate normal distribution. Okay, and then we will mention some issues that are specific to the Bayesian graphical modeling framework. And the main one is how to design priors for the parameter theta k, which must satisfy the conditional independencies in a graphical model setting that are specific of the model, the graphical model under consideration. Okay, so this will be the first difficulty, and there is a huge literature on this kind of issue. Okay, well, the second issue is something which is instead more common even to score-based frequentist methods, which is related to the number of models, of competing models that we need to evaluate, which means that in practice we cannot evaluate this posterior in an exact form because we don't have the denominator. We cannot compute the sum with respect to all possible models, but we will need to implement some approximate strategy in order to compute an approximate posterior probability for the model MK. Okay? So in general, this will be the target, a posterior probability for a model, a DAG model, a UG model, that we will try to approximate using some kind of Bayesian strategy, for instance, based on Markov chain Monte Carlo. Okay, I think we can stop here, okay, for the lunch break, and then we meet again this afternoon.